All right, hello everybody. We're going to go ahead and get started. Welcome to the inaugural Robotics Careers Pathways Seminar. Did I get that right? Robotics Pathways and Careers Seminar, speaker series. I'm Professor Chad Jenkins. I am the Associate Chair for Michigan Robotics. I'm also in charge. I'm the Program Chair of the Undergraduate Program, and I welcome you to our inaugural event. Part of the reason why we have this event is because since we've started the robotics undergraduate program here, started a major, the question that I always get from students and parents is, what can I do with a robotics degree? This robotics sounds cool, it sounds awesome, it sounds great, but what kind of job can I get? What can I do in my career? And so because robotics is a new major, we're on the cutting edge. There really no other schools that are doing it. They're doing robotics in this way. That we are really out there. We are trailblazers. We're pioneers. There's not really a lot of examples to go from, but there are amazing roboticists that are out there that can give you an example. That can show you where things could go. And so we're going to have a great speaker series. It's going to happen we're going to do it bi-weekly. Our next speaker is going to be Ryan Eustace, who leads Toyota Research, and he'll be speaking on the 22nd. We're very privileged to have Mario Santillo from Ford, who's going to be our inaugural speaker. And so this will just be a way to just give you a sense of what is out there, what are the possibilities. And so we're going to go ahead and before I hand the stage over to Mario to give a sense of his experiences and the possibilities, I just want to hand it over. I want to introduce our undergraduate coordinator for robotics, Kayla Dombrowski, that has a few announcements.
Hello, everyone. We do have some seats up in the front row if you'd like to move up and have a table. But my name is Kayla Dombrowski, and I'm the undergrad program coordinator for robotics. We currently have 3 majors. And we're happy that you're all here. We have, if you're interested in declaring and you're ready to declare a robotics major, we have a robotics signing day, which will be September 16th at 3:30. It's going to be a big celebration. Please come. You can look on U of M sessions. So that's where you can register for the event. And we'll confirm your eligibility, and then we'll send you an invitation. We also have, like Professor Jenkins said, the speaker series. You'll continue to see emails about who we'll be having come and invite to talk about their robotics career and pathways. And again, we have a bunch of advising appointments available if you'd like to register. I will be sending out that QR code as well. Okay.
All right. So if you're interested in robotics, please let us know. We can declare, and even if you're just interested in talking about possibilities, we have advising appointments. So with that, I would like to hand the floor over to our inaugural speaker, Dr. Mario Santillo from Ford. He has degrees in aerospace engineering from Rensselaer Polytech. He is an alumnus of the University of Michigan, where he got his PhD. Go Blue! I just want to add that. He's been working at Ford Motor Company, leading a number of their research projects over the last 11 years. And most importantly, is our neighbor upstairs on the 4th floor. So the 4th floor has a number of great people from Ford Motor Company, a number of amazing research projects. And so he's one of our key people that really is helping us build a great bridge and create new opportunities for students in robotics. And so with that, I will hand the floor over to our inaugural speaker.
All right. All right. Thanks, everybody, and welcome. Very happy to be here. So as was said, I'm Mario Santillo. I work for Ford Motor Company, and I actually lead a lot of their robotics research. And I've been doing that for the last 4 years, but that's not at all kind of how I got here, was not robotics. When I was a undergraduate, I actually went to undergraduate at Rensselaer Polytechnic Institute, or RPI. If anybody knows, that's upstate New York, much smaller school than U of M. But I did aeronautical and mechanical engineering, because you couldn't actually have just an aeronautical or aerospace engineering degree at the time. That was great, but what that actually led me to was I went and then did some internships and co-ops with Boeing out in Southern California, where I learned a lot about spacecraft guidance, navigation, and control. And that was really my first intro to what controls is. And what I found is I actually did 2 co-ops and 1 internship with Boeing kind of over a series of several summers. And I realized that I had absolutely no idea what I was doing there, but I figured I could actually do it really well, even though I had no idea what I was doing. And it wasn't until the 3rd summer, which was actually after my senior year in undergraduate and before I started here at U of M, that I realized how to put 2 and 2 together and realize what my teaching in undergrad actually led to what I was doing as essentially a full-time job at Boeing. And that really led to a lifelong passion for controls. And I came here to U of M for my master's and PhD, where I worked in the aerospace engineering department and focused on flight dynamics and controls. After that, I ended up, well, actually, I'll take a step back here. What I really liked about aerospace engineering was it was super multidisciplinary, just like robotics. And I took classes in electrical engineering, I took classes in mechanical engineering, industrial and operations engineering, math, of course, aerospace engineering. And it was really neat that I had no idea that this was all setting me up for where I am today. Ultimately ended up at Ford, but when I started at Ford, I wasn't doing anything close to robotics. I was doing automotive emissions control. So you learn how to model like a catalytic converter system and then how to make better emissions, better fuel economy and stuff like that. But the last 4 years, I've been working in robotics, and it seems like a huge transition, but it actually wasn't that big of a transition overall because of all the things I had done in the past. So we work on a lot of different things at Ford. So you see like the agility robotics, digit biped robot. We have several of those that we're working on integrating these walking platforms with autonomous vehicles to be able to do a full end-to-end, fully autonomous package delivery. And you'll see we're working very closely with Professor Grizzle and Professor Vasudevan down in the lab down here to make these things actually useful for the consumer at the end of the day, because they're not extremely robust. You also see a lot of wheeled platforms that we have here, including stuff in our manufacturing facilities. Also the Boston Dynamics Spot robot that we've named Fluffy. And it's actually paired with figuring out how to make robots do the best thing in the best use case. So walking robots can get over things like wire bundles and cross transfers and train tracks and things that you can't drive a wheeled robot over. So how do you coordinate the 2 different things together? Almost the entirety of last year, I actually spent in the manufacturing facility. I facilitated the manufacturing launch of our F-150 Lightning here at the Rouge Electric Vehicle Center, which is an entirely brand new building that we brought up right next to the Dearborn truck plant where they produce the gasoline and diesel F-150s. This was a really, really cool experience. I've been working within manufacturing technology development for a number of years, but I was never actually in the plant until last year, at least full time. And once you see the rubber meet the road, there's a lot of really cool opportunities for robotics and automation in general. So I think that's what I want to touch on. And I know the title of the talk was originally The Future of Manufacturing Automation. That is true, but I want to talk more about how I got here and the things that I think will help you along the way, because I don't have a robotics background specifically, but I work in robotics now, and it really is not nearly as much of a hard transition. I will say, given that, if I had a program like this when I was in undergraduate and graduate school, it would have been extremely helpful for where I am right now. So the other bit too, clearly FRB, just a plug. We are up on the 4th floor. We have about, I don't know, there's about 100 engineers assigned here. I know we're like ghosts that we're almost never around. It's a really cool playground up there. If you guys get a chance sometime, come stop by, ask us to see the place. I mean, it's not very secretive, even though it seems secretive with like the opaque windows. We're more than happy to like show you around and see a lot of the same things we have right here going on. So lots of cool things. So I want to start a little bit about just robotics versus robots. So we all know what a robot is, right? It's this physical implementation, this thing that moves around and does things that we ask for it to do. But this gets back to what I was talking to the multidisciplinary nature of robotics, and all the things in colored boxes here are just, some implementation of what we would call robotics, where we're using sensing, right? This could be cameras and LiDARs and a bunch of other things, right? Ultrasonics and different types of cameras. And processing that data in a way through a perception system to essentially understand the world and where we live in. And then we want to use that to achieve some objective, right? We want to plan a path. Are we moving a robot, like a robotic arm, in many degrees of freedom? Are we moving a mobile robot? Do we have obstacles to avoid? How do we actually plan the path? And then the controls, which is where my original discipline was in, is how do we execute that? And how do we do it robustly and make sure that the robot doesn't fall over and do weird things? Obviously, there's a huge interaction with human interaction. So human-robot interaction is a primary piece, because when we think about manufacturing facilities, it's great to have robots caged off, but they take up a lot of space. It's hard to reconfigure them. We want to get humans operating very closely with robots, and that means that we need to really understand well what's around us, because robots could be extremely harmful if they met you in the wrong situation. So we think about this kind of a different way too. So we think about this in a software stack view, where at the bottom we have our hardware layer, where we have sensors and compute, and then you have an operating system on top of that, a middleware, which kind of just is the tie that binds everything and makes it really accessible to get up and running fast. I'm sure a lot of you know a lot about ROS. And then on a high level is the application layer, where the algorithms are. So these are all the things that people think about, right? Artificial intelligence, reinforcement learning, actual controls. We spend a lot of time on algorithms, but the rest is super important, and to make it work very robustly in the end. So pivoting a little bit into manufacturing, I wanted to talk, you may have heard Industry 4.0. So Industry 4.0 in the most basic sense is really just trying to make a factory smart. So they have this industrial Internet of Things, which is essentially just a smart word for a very expensive sensor. Artificial intelligence, cyber physical systems, so that's like augmented reality, virtual reality, digital twins of systems. And you want to get these all connected together. So this is a huge system integration exercise, but the whole purpose is really this no surprises manufacturing. In manufacturing, you don't want to have surprises because it costs downtime, and downtime costs a lot of money. I mean, just a minute down in the manufacturing line could be tens of thousands of dollars of wasted profit. Clearly, quality improvement, the more you get these things to self-monitor and then self-optimize, the more you can reduce all of these. So a lot of what we're working on in the manufacturing space is towards this end of not using the picture you see in the middle here. These are all robots that have no ability to sense anything around them. They are just pre-programmed to go to a very specific location and do a very specific task. It takes an immense amount of time to program all those joint angles. And in fact, if you go into most manufacturing facilities and you ask for, the resident roboticist, he's the guy who knows how to program these computers, which is essentially programming joint angles and motions in a very specific open loop fashion. And to put these things up and running can take months and months and months. there's a better way to do it, and it requires us becoming a lot smarter about how we program these robots and interact with them. And this is what we're hoping you bring up the next generation. So when somebody goes into a manufacturing facility in 10 years and say, bring in the resident roboticist, it's not the same person that's doing this job. It's a totally different job. We can transform that entirely. So manufacturing has kind of come along a long way. And I think process automation in general is really going to continue in a bunch of different areas in manufacturing. In fact, all different areas in manufacturing. I'm going to point out a couple different examples here. Oops, sorry. There's this top right picture is supposed to be animated, but it's not animating right now. What it actually is it's an industrial robot that has some force and torque sensing on the end effector, and it's actually using machine learning methods to teach itself how to automatically install a torque converter into an automatic transmission. This is actually something we have running in our Livonia transmission plant just down the road here. So that's nice because to install an automatic torque converter, it's a spline fit. So you have to push down with a certain amount of pressure. You have to turn it along some splines. You hit another detent and it drops in. Then you have to turn it again. And it's not easy to do and very difficult to have a robot learn to do it without breaking the thing. So using machine learning, we were able to teach the robot to do this effectively, and it really reduced the downtime and the waste of learning. Let's see here. Nope. I am clicking on it, I promise. Either way, that's the only animation on this page anyway. So lots of other things though. So autonomous robots for material delivery. You see like the AutoGuide mobile robot in there. Using these to autonomously deliver goods to the line side. These are just big mobile robots just like you're using in your class, right? So these have essentially a LiDAR up at the top that's using a map to guide along a mapped route. Alternatively, we have these autonomous guided vehicles that we're using to build the F-150 Lightning. So this is an actual shot of the plant here in Dearborn as of probably late last year, where we had these vehicles going down the manufacturing line, sitting on top of these AGVs, we call them. And I mean, these things are massive, massive vehicles. They can carry a ton of weight. And we need to figure out how do we make these things operate robustly, because any downtime here costs a lot of money. You can't afford for these things to not work well. So interestingly, what I found is the next wave of manufacturing automation is actually influenced by a bunch of advances in technologies that are completely outside of automotive. So for example, material handling has really benefited from all this warehouse and delivery management. So this is like an Amazon warehouse. But the necessity cropped up here immensely from online ordering businesses, right? So these were all enabled by advances in a bunch of different technologies, right? Artificial intelligence, batteries, wireless communication, sensors, perception and control, open source software frameworks. I'm specifically referring to stuff like ROS and things we can download on GitHub and get up and running really quick. This is a totally different methodology than the way we used to think about things, where everything needed to be developed in-house, and if it wasn't in-house, it wasn't good enough. So really taking advantage of quick turnaround of software here is key. And all of these pieces here that I'm talking about are central to the things that you'll be learning in the robotics degree program. And so all of this put together is really a huge push for robotics. So I'm going to talk just a little bit about sensors and perception and control, because that's kind of where I come from. So one thing when we think about robots, if you look at almost any of the robots that you're going to see in this building here, they are almost entirely self-smart. They're self-aware of the environment around them. And this is just like an autonomous vehicle. So any autonomous vehicle you see driving around here, they've got tons of sensors all over the vehicle. And that actually leads to them being extremely expensive. They take a lot of compute power, which takes a lot of energy, and that reduces your uptime and adds a ton of cost. So where we actually see a lot of this robotics going and where we're moving it forward is offloading a lot of the compute and offloading a lot of the sensing more to the infrastructure and essentially making the infrastructure smart, where we can now utilize resources much more economically. But that's only a piece of the puzzle, right? So we can make these things a little bit cheaper, which means that we can do them at more scale faster. And so one example of this, so here's an AGV that we use in our stamping plant in Dearborn. So this is where they take, this AGV is actually massive. You can't really see the scale so well here, but this thing will come up and it'll take a 20-ton roll of sheet metal and move it from location to location. So picking up 20 tons at a time. These sheet metal rolls are enormous. So they'll first go into a stamping press, which just takes out like blank flat die pieces. And then those will go into another stamping press that actually form the sheet metal, which become the pieces of your car that then get welded together in that other where you saw the robots welding in the prior slide. So these AGVs, they're self-aware. They have 2D LiDARs all around the bottom. They have other 2D LiDARs looking in a different plane to just make sure humans aren't around, that they're not going to run into overhead obstructions or anything like that. I mean, clearly the momentum that goes along with something that's carrying 20 tons is massive. This thing doesn't need to be moving fast to kill you because the momentum alone will take care of that. So when these things move into different areas, imagine it's docking over in this area, there might be obstructions in the way. And as it moves, it dynamically changes all those obstructions. So you can't see what's behind here necessarily in all cases. I mean, it doesn't need to be that tall to obstruct these scanners that are only 6 inches off the ground. And that screws up a lot of things. So imagine what you can do if you just have simple overhead sensing that looks around here and it fills in all the blind spots. Lots of opportunity for improvement. So another bit is just, I want to point out the numbers here. Material handling is only about 1/4 of the total factory workforce, which I say only, but I mean, that's still a significant amount. Just moving goods around. And they say 40% of the cost of a vehicle that you buy off the lot is the cost of just moving material around. That's a huge, huge cost. So tons of opportunity for save here, but only a tiny fraction, right? So at best 1/20th of facilities are actually using autonomous robots in the entire market. Lots of opportunity for improvement here. So all of these things can be associated with material handling, but I just want to point out a lot of advances. So digital twin generation. So this is actually a high resolution 3D point cloud image that we generated of our advanced manufacturing center in Redford, Michigan, where we actually automated a robot. So it was a combination of Spot and this black and yellow ClearPath robot you see here to go around and automatically choose locations of interest and generate high resolution 3D point clouds, which can then be used for all of your robot mapping or other facility needs. I already talked about autonomous material handling, but then there's also a lot in terms of this infrastructure sensing that I was talking about. So imagine these industrial robots. So this top right picture here is an industrial robotic arm with a human standing essentially in its path. And you see that it's essentially looking how close the human is to where the robot is going to be in the very near future. So you want the robot to make sure that it stops because these robots can move, say, 8 meters per second. You need it to stop in time before it hits you. The idea is that we can never necessarily prevent you from walking into a robot, but we can guarantee that a robot will be stopped before you walk into it. So these are really complicated problems. They require a lot of brain power to solve. And there's major work to be done in making all the robots for the industry safe and effective. So all of the groundwork is being laid right here in the curriculum and all the research going on at U of M. This is a major reason Ford is so interested in partnering with University of Michigan, because we need to move this faster. We can't wait for everything to just be done and on the market already, because we'll be way behind. We need to adopt these technologies as fast as we can make them and partner with the universities to be right at the forefront of making them. I mean, think about a lot of the challenges that you can work with. Just take any robot we're thinking about, right? There's going to be random objects in the way. How do you get around them? There's going to be stairs. There's going to be bumps. There's tiny narrow hallways. If you have narrow hallways and the sensors start to conflict with each other, the robots just stop and stare at each other. How do you get across that problem? There's obviously dynamic environments that require sometimes different tasks and complex tasks. Do you have a question?
I just wanted to make a quick comment, because I don't know if people realize that, but that picture, that's the digital twin generation. I just want to make clear that that's not a picture that somebody took.
Right.
That is a 3D model that was built by those robots. And what you're seeing is just a rendering of that 3D model.
Yep.
The robots built all of that, and it looks like, and I'm in my 40s, so I might be seeing it really, but that looks like a real image, and robots can build that up just from the perceptual capabilities. And I think that's pretty amazing.
Yeah, it is pretty amazing. And I'll say it's colorized because there is also a camera on there. So you add in the color to the point cloud. So anyway, but I mean, we do this with all of our facilities. And I mean, I'll expand on that for a minute. It costs hundreds of thousands of dollars every year per facility to bring somebody in with a high resolution surveying LiDAR mounted on a tripod and put it down, step away, have the thing scan for about 2 minutes to generate this high resolution point cloud, walk about 10 feet, put the tripod down in another spot, hit a button and walk away. I mean, perfect opportunity for automation. So I use automation a lot more than robotics, but they're really the exact same thing. We're automating these machines to do the things that are more desirable. We're taking humans away from very arduous and boring tasks, and we're giving it to the robot. And it's not necessarily about replacing humans. It's more about augmenting humans so that we're all doing a better job at the end of the day. So also along with this is perception and control algorithms. So I've said these challenges are becoming increasingly complex. So we're at the algorithm layer at the very high level of how do we make the algorithms do what we ultimately want? And what I find is that the algorithms come from a variety of domains. So at Ford, we don't have many people who are classically trained roboticists, but what you'll find in the robotics group is you have a lot of people that have a controls background, you have people who have a physics background, you have people with a computer science background, and you kind of mash it all together and figure out how to make it work. And sometimes we don't all talk the same language and we have to come up to speed. So this is a fantastic opportunity to be able to come on common ground with language. And so you guys will be a step ahead when it comes to solving these challenges in the future. You'll see more and more industry is internalizing the expertise for the system integration, because ultimately robotics is a giant system that needs to be integrated and a lot of pieces need to come together. And it's very, very difficult to do if you are pigeonholed into one very specific area. So, I mean, I just look at stuff like this graph theory. So this could be like a traveling salesman problem where we need to find the path with minimal time, but maybe there's charging that you have to go back and forth to. Maybe there's multiple robots. Maybe you have robots riding on other robots. So, you know, you have like a multiple traveling salesman problem with a bunch of different constraints. Really difficult problems to compute, especially in real time. Then I look at this other stuff where I think about collision avoidance. So the Arc de Triomphe in Paris, people are probably driving around this right now. People navigate this all day, every day, and it's a total disaster. So, I mean, if we just look at this vehicle right here, we wonder, well, what's his intention? Is he actually trying to get out here? Is he getting herded by the other vehicles? Is he trying to go out this way? We don't know. Imagine if these were autonomous, but they're decentralized. They don't necessarily know what the other person's trying to do. How do we actually coordinate this down into a problem that we can understand. So we think a lot about this. I mean, people clearly do this all day, every day. So we know it's possible. How do we make algorithms do this? But when we look at this, drivers cooperate and compete at the same time. And this creates really complicated feedback loops. And so what we're trying to do here is another animation that won't play, but these circles represent some objects, and they're just going from a beginning point to an end point, and they're not going to collide with each other if you watch the animation. But we're trying to essentially boil problems like this down into simple problems that are solvable so that we can understand the underlying physics and then put it back together into something that actually helps us in the long term. And I think I'm coming to the end here. So long story short, the technology is changing. We need new people with new learnings to be able to really push the next generation, I'll say, of automation. I mean, this says manufacturing automation. It's really the next generation of automation and robotics. There's a lot of really cool and interesting problems. Human-robot interaction, I mentioned at the beginning. Increased autonomy at increased speeds, right? So if we can go slow, that's a really good starting point. That's a lot safer, but immediately you're going to want to increase that speed because you can get more throughput from it. Integrating AI. How do we integrate AI with a system that you have to guarantee safety when you have no idea how to explain what the output of the AI is? So how do you integrate those really well? Real-time feedback, tactile gripping. So how do we do this in a generic way where we can grip objects without breaking them, but maybe they're heavy and maybe they're fragile? Very, very difficult to do in a generic way. And I think if you guys look around here, you'll find a lot of different professors in this building alone working on all of these different challenges. And this is exactly what we're hoping to bring together. So with that, I guess I'm done with the official presentation. There's 2 videos here, which would be kind of cool to show. I'll explain through. So this agility video here is about essentially, it was a promo video. You can actually find it on YouTube, but this was our demonstration of integrating this robot with an autonomous vehicle to be able to do fully autonomous end-to-end package delivery. Up here is a little bit newer thing where we integrated this KUKA robot. So it's an autonomous mobile robot base, but it's also got a robotic arm on the top of it. And it was integrated with our 3D printer system at the Advanced Manufacturing Center. So this is actually the exact same place where you saw the high rendered 3D point cloud, where we designed this robot to be able to go up and tend to all of our 3D printers. So if you've ever 3D printed something where you have all the support material, you need to take the 3D printing plate out and then put it into a washing machine, and that takes some amount of time, and then you have to put it into a drying rack. So this is automating that entire process. You have to integrate with the 3D printer. You have to open the door. You have to grab the stuff out. You need to put it into drying, and then you need to grab others and put it into the washer. When that's done, it needs to go back drying. We employ a whole staff right now that runs this facility 24/7 that just go do these and change them in and out. We can now do it robotically, which is really neat. So these are some of the neat things my group gets to work on. Like I said, if you're interested, come up and join us. Yeah, I will try here. Maybe not. Nope. It's all right.
Well, let's thank our speaker. So now